This section discusses how the volume and velocity of data can shape your pipeline. Volume and velocity requirements drive infrastructure decisions across all pipeline layers. Although they are different measures, you need to look at them together to determine how your pipeline needs to scale. You need to scale to handle ingestion and storage of the amount of data at the pace of its arrival. You also need to consider how long data should be stored to balance cost and availability. From the processing standpoint, you need to understand how much data must be processed and analyzed to address a singular business problem. You also need to know how quickly the data must be processed after it arrives in the pipeline. In terms of visualizing data, you need to understand how much data consumers need to access at one time and how frequently new data must be incorporated. The next few slides give examples of the types of decisions you will need to think about that are related to volume and velocity. To choose ingestion methods for your pipeline, you need to understand the volume of data it's expected to handle at a given interval. For example, you might need to ingest a continual stream of large volumes of small records that need to be processed as quickly as possible. Or you might need to ingest larger individual records that arrive periodically and are stored to process as a batch of records. Both of these examples include high volumes, but the velocity of their arrival and the speed with which they must be processed impact your pipeline design. Your storage decisions will be closely tied to ingestion methods and the volume and velocity of incoming data. You will also need to consider how the data will be accessed. For example, will it reside in storage for periodic access over a long period of time, or will it be stored only briefly before it loses value? The distinct needs for processing high volumes of data, that is, big data, have been the driver behind big data frameworks, for example, Apache Hadoop and Spark. These frameworks are designed to process really big chunks of data very quickly by using a distributed system. The volume, frequency, and type of processing that you need to do to find business insights might lead you to use a big data framework. Analysis and visualization tools must match the volume and velocity of the data being ingested and processed. Visualizations that aggregate data must be able to scale to match the volume of data that is being analyzed. Elements that must be reviewed in real time need to be made available in tools with low latency. Here are a few key points to summarize this section. Volume is about how much data, and velocity is about the pace of data. Together, they drive the scaling requirements for your pipeline. When you build your pipeline, consider volume and velocity at each layer. For example, some data that arrives at high velocity doesn't need to be processed immediately and can be stored and processed at a slower pace. Your choices should balance costs for throughput and storage against the required time to answer and accuracy of the answer. This section discusses the variety of data types that you will need to use in your pipeline. In this section, you will learn about a few general data types. This section will be followed by one about data source types. These sections will help you start to think about how these characteristics will influence the decisions that you make for your data pipeline. You can separate data into three general types: structured, semi-structured, and unstructured. Structured data is probably what you think about when you hear the word data. Structured data is stored in a tabular format, such as records in a traditional relational database. Data is organized based on a data model, which defines and standardizes data elements and their relation to one another. This makes structured data easy to query, but not very flexible. Structured data is referred to as being hot, meaning that it's immediately ready to be analyzed. Semi-structured data has a self-describing structure and recognizable elements, but it doesn't have the rigid schema constraints of structured data. For example, a JSON or XML file is semi-structured. You can think of semi-structured data as lukewarm. Some data will be ready for analysis immediately, but it's more likely that the data needs to be cleaned or pre-processed before you can analyze it. Unstructured data doesn't have a predefined structure. This makes it very flexible, but more difficult to query. Unstructured data is considered cold and takes the most work to analyze. Historically, much of the available data and most of the data used in decision-making has been structured or semi-structured data. For example, analysts writing SQL queries against a relational database. But the explosion of data that has been happening has been with unstructured data, such as clickstream data, social media posts, video and image files, and sensor data. Therefore, the focus for a lot of new data infrastructure is on pulling the value out of unstructured data. But as you learned, getting at that value is challenging. That's where organizations will want to innovate with artificial intelligence and machine learning, or AI/ML, to tap into new insights. This slide lists a few simple use cases for the data types based on customer service data. A structured example is querying a relational database to report on customer service tickets. A semi-structured example is analyzing customer comments that are stored in JSON files. The unstructured example is to use an AI tool to perform sentiment analysis on customer service emails. Here are a few key points to summarize this section. The three general types of data are structured, semi-structured, and unstructured. Structured data, such as a relational database, is easy to query and process, but not very flexible. Unstructured data, on the other hand, is very flexible, but more difficult to work with. Most of the data growth in recent years is of the unstructured type. This section discusses the variety of data sources that you might use to fill your data pipeline. Now that you have looked at how data might be structured, you want to consider the characteristics of the data source itself. Your pipeline might need to combine data from many different sources and pull them together as a new data source to be analyzed. Three common types of data sources include your organization's own databases or file servers, public data sets about a topic of interest, and data generated by events, Internet of Things or IoT devices, and other sensors. You will need to perform discovery activities that are specific to any data source that you plan to use. But here are some general considerations by source type. Data sources that are under your organization's control might be structured sources that are ready for analysis in their raw state without any additional massaging of the data. Be cognizant of any personally identifiable information that might be part of the data store. Services are available to load data from on-premises resources into your cloud pipeline, but this might be an opportunity to migrate an on-premises data store to the cloud. Public datasets are often in a semi-structured format and probably contain elements that you don't need and therefore want to discard rather than store. You will also likely need to transform the data to merge it with your own datasets. Event, IoT, and other time series data requires your pipeline to handle streaming ingestion, and you will want to choose a data store that works well for time series data. These types of data sources lend themselves to real-time processing so that automated actions can be taken based on some event or threshold value. This slide lists a few simple use cases by data source type, using the example of healthcare data. The examples highlight how the data might be combined to help customers. Data from the on-premises database could be queried to find patients who are overdue for a visit. By using public healthcare datasets, the company might combine public health data that identifies demographic risk factors for heart attacks with customer data to personalize information for a patient who shares the risk factors. If patients had a mobile app that sent real-time heart monitoring data at some interval, the data could be evaluated for anomalies that coincide with known risks. Then, the patient or their doctor could be alerted. You can see in these examples how pulling data from many sources can provide different levels of personalization and prediction. Although there are benefits to being able to pull from different data types and sources, there are also challenges. The available data type might limit the types of analysis that you can perform. Pulling sources together complicates ingestion and processing and might make it more difficult to manage the veracity of your data. Here are a couple of key points to summarize this section. Common data sources include an organization's own databases, public data sets, and time series data such as events, IoT data, and sensor data. Combining these data sets in your pipeline can enrich your analysis and the decisions that you can support. But complexity also increases because you must manage the differences in structure and content between each data source. This section discusses considerations for data veracity and its impact on value. It might seem obvious, but it's important to remember that the impact of bad data can be worse than working without much data. When you work with limited data, decision makers are aware of the limitations and can manage risk accordingly. If consumers trust bad data to drive decision making, the results could be dramatically different. Data veracity is contingent on the integrity of the data. You might need to determine the integrity of the data source and adjust any areas where that source might lack integrity. Data changes over time. As it is transferred from one process to another and through one system and another, there are opportunities for the integrity of the data to be negatively impacted. You must ensure that you maintain a high level of certainty that the data you are analyzing is trustworthy. Understanding the full life cycle of your data and knowing how to protect it effectively will greatly strengthen the integrity of your data. As part of data discovery, you need to assess how good the data is to start with. As part of ingestion, clean and transform data to make it usable. After you ingest the clean data, protect it where it's stored and in each step of its processing. The first step to understand the trustworthiness of your data is to get more familiar with the dataset's characteristics. For example, how old is the information? Does it seem like the dataset is missing information? What do you know about its lineage? That is, do you know what changes or transactions brought it to its current state? If you have a question about the data, can you go back and understand how its current value was set? A lack of lineage also makes it more difficult to address potential issues such as ambiguity. Does this value refer to Paris, Texas, or Paris, France? And statistical bias, or the data set isn't representative of its population. The level of discovery that you do will depend on what you know about the data source. You might actually perform processing or analysis on the data to help determine its veracity. After you have a better understanding of the source data, you can take steps to improve its current state and prevent it from becoming untrustworthy. As part of ingesting the data, identify and remove duplicates, find outliers in the data, and resolve differences in how different sources represent the data. To protect the data's integrity, you want to prevent software bugs from reintroducing what you removed during cleaning. You also want to prevent unwanted changes, whether they are an intentional disruption such as a hack, or a mistake made by someone who has access to update the data. Even where you can't prevent mistakes, introduce appropriate data audits so that you can maintain lineage of the data after it's in your pipeline. Here are a few key points to summarize this section. Veracity is about trusting your data, and without veracity, you can't expect to get good value from your data. For each data source, you need to discover its veracity, clean and transform what you can to improve it, and then prevent unwanted changes after you have cleaned it. This section discusses considerations for data veracity and its impact on value. Let's look briefly at the activities that you might perform to address each of these categories. You will go deeper into these topics in other modules in the course. To evaluate the state of the data, you must ask the correct questions and dig into the dataset. You will want to wear your data engineer's hat to think about the mechanics and technical requirements for the data, and your data scientist's hat to really identify whether the dataset will be valuable even in its cleanest form. When it comes to cleaning your data, the first step is to come to a consensus on what clean looks like. Some businesses deem clean data to be data in its raw format with limited business rules applied. Others might consider data to be clean only after it has been normalized, been aggregated, and had value substitutions applied to regulate all entries. These are two very different understandings of clean. Be sure to know which one you are aiming for. As you find errors in the data, trace them back to their likely source. This will help you with lineage and to predict workloads that will have integrity issues. It will also help you make a case for changes to an upstream system to improve the efficiency of ingesting the dataset into your pipeline on a recurring basis. When you do need to change values in a field to use it, make sure that you understand the impact. For example, from a purely data-centric view, entering a 0 in an empty column might seem like an easy data cleansing decision to make, but null might not mean 0 in the source that you are using. Similarly, data fields that sound like the same thing might actually be different. In some systems, the original data is no longer valuable after it has been cleaned and transformed. However, with highly regulated data or highly volatile data, it's important to maintain both the original data and the transformed data in the destination system. For example, in an online gaming system, there might not be value in recording every direction shift that a player makes as they move on a map. The only important value is when the player enters or exits key areas of the map. However, in a banking app, all details of every transaction are vital for auditing, even though a customer might only care to see if their transaction was successful or not. Even if each data source has been carefully maintained, sources will have differences that you need to address with transformations. Transformations are likely to occur across the ingest and processing phases, and the types of transformations might be quite diverse. Transformations can be basic, such as the example pictured on this slide, where you need to convert field values to a common format. In this example, the database record is transformed to replace the null value with a 0 in the children field and replace the word Ohio with OH in the state field. Transformations can be more advanced, such as applying business rules to the data to calculate new values. Advanced transformations include filtering records, complex join operations, aggregating rows, splitting columns, and data validation. A common approach with applications that aggregate data is to make updates directly to the aggregated value. For example, a count or average. Reporting and business intelligence, or BI, tools query the database and have access to the aggregated value. In this example, the business is interested in learning where users spend most of their time while on this website. To support this, their extract, transform, and load, or ETL process, ingests page view stats daily and updates the daily average for each page in their analytics database. As the slide indicates, there are shortcomings to an approach of saving only the aggregated values. First, this approach is not flexible if the business decides that they want to dig deeper or ask different questions. Second, the analytics database doesn't have any traceability back to the previous day's value after the new day's data has been incorporated into the average. Finally, this approach makes it more difficult to find and debug errors. In this example, the total of 960 seconds for page Y is incorrect, but there isn't a way to easily figure out what is causing the error or to audit it. This slide highlights a better approach for analytics to support the value and veracity of data. The ETL process writes a row in the analytics data store for each page view and includes a timestamp. This gives the business the opportunity to query the data in different ways and retains the original values so that queries could be done for different time periods. This approach also provides traceability to the original values and makes it easier to debug problems when errors occur. In this example, something went wrong when capturing the value value for October 5th for one of the users. But because you have the details for each day, user, and web page, you can identify that the data is missing. By using timestamps and capturing as much unmanipulated data as you can, you provide flexibility and traceability in your analytics solutions. Now that you have clean, trustworthy data in your pipeline, it's your job to keep it that way. This means preventing unwanted changes, knowing what has changed, and putting rules and processes in place that limit the opportunity for issues to be introduced. You need to secure your pipeline layers as data moves through them and when data is stored in them. Use the best practice of granting least privilege access to any users who should be allowed access to the data. For example, many users will only require read-only access. Different types of data stores will have different methods to maintain data integrity, and you need to implement the recommended best practices for each type. It is also important that you implement audit trails so that you can trace back any changes. At an organizational level, the organization should implement an overarching data compliance and governance process that applies across all of the data stores and access methods. The governance process should include classifying data according to its security level and cataloging data to make it findable. An important part of this approach is maintaining a single source of truth for an element of data. This means that one data store is the system of record, and any other data stores that use that data load it from the primary source. Here are a few key points to summarize this section. As a data engineer or data scientist, you need to question the data source before it ever enters the pipeline. After you determine to use a data source, you need to determine how to clean it and have a common definition of what clean means for a data source. Ensure that any transformation does what you intended. Save raw data in an immutable form so that you have details instead of only aggregated values. This supports future insights and makes it easier to find errors. To protect your cleaned data, your organization should implement processes and governance strategies to manage the data in your systems. This section summarizes what you have learned and brings the Elements of Data module to a close. The module introduced a basic vocabulary to think about the data sources that will feed your pipeline. You learned about volume, velocity, variety, veracity, and value, and how each of them impacts your pipeline design. You also learned the importance of asking questions about data sources before they enter your pipeline and protecting them after they are part of your system. Here is a sample exam question for this module. A data engineer has been asked to develop a pipeline to analyze partner sales trends by using sales transaction data. Each sales partner provides a CSV file each month. Although the files contain similar data, they are not in a standard format. Which option is the most effective approach to collect this data for a data analytics pipeline? What are the key parts of the question? Here are the key words and phrases in the question. The question notes that the pipeline will use sales transaction data that is received from multiple sales partners. The data that needs to be collected into the pipeline is not in a standard format. Now, let's look at the answer choices. The possible choices include A. Extract the number of sales from each partner file. Then, write the partner ID and sales total to the analytics data store for analysis. B. Extract the data from each partner's file and transform it into a uniform file structure before writing it to the analytics data store for analysis. C. Identify sources of statistical bias as part of extracting and transforming the data for analysis. D. Import all of the files into the analytics data store with the partner ID. Grant access to each partner to edit the records and fix errors in only their data. Based on the keywords that were identified in the question, Which answer is correct? We'll pause for a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. The correct answer is B. Choice A, extract the number of sales from each file, then write the partner ID and sales total to the analytics data store for analysis, does describe a way to combine the data and record summary sales data, but the best practice would be to write the detailed record to the analytics store for both future analysis and auditability. Choice C, identify sources of statistical bias as part of extracting and transforming the data for analysis, is not a relevant consideration for sales transaction data. It also isn't a process that you would perform as part of collecting data from its source and bringing it into your pipeline. Choice D, import all files into the analytics data store with a partner ID, then grant access to each partner to edit the records and fix errors in only their data, isn't a good approach because it goes against best practices to protect the veracity of data in your pipeline. You might also ask partners to fix errors in their source databases if appropriate, but you don't want people modifying the data in your analytics store. Avoid giving write access to your analytics store to reduce the chance for human error. To use the data from partner files in the pipeline, you need to define a unified structure and transform each partner file into the common structure. So B is the correct answer. That concludes this module. The Content Resources page of your course includes links to additional resources that are related to this module. Thanks for watching.
Welcome to the Design Principles and Patterns for Data Pipelines module. This introduction section describes the content of this module. This module builds on the introduction to data pipelines and the elements of data that were presented previously. The AWS Well-Architected Framework is a key resource which you can use to design new pipelines or improve infrastructure that you are asked to work with. Understanding the evolution of data stores will provide context for the modern data architecture which is presented in this module. The modern data architecture provides a framework to plan a holistic solution that addresses the concepts of modernize, unify, and innovate, which are described in the Data-Driven Organizations module. Understanding key characteristics of streaming data pipelines will also provide context for many of the concepts and use cases presented in other modules. The objectives of this module are presented across multiple sections, each presented in its own video. The module wraps up with a sample exam question. This section introduces the Well-Architected Framework as a tool to design modern data architectures and analytics pipelines. The AWS Academy Cloud Foundations course introduced the Well-Architected Framework. The framework is available on the AWS website, and you can find the link on the Content Resources page in your online course. You might find it helpful to open the website now to look at the way the pillars are organized. The framework comprises 6 pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability. The framework provides best practices and design guidance across each pillar to help you make choices and review existing architectures. The Well-Architected Framework includes lenses, which extend the guidance to specific domains. You'll find a list of the lenses on the main Well-Architected Framework page. The Data Analytics lens helps you learn the key design elements of well-architected analytics workloads and provides recommendations for improvement. The lens also includes reference architectures for common scenarios. The ML lens calls out differences between non-ML and ML applications and includes a recommended lifecycle for ML applications. The ML lens is discussed in the Processing Data for ML module. Here are a few key points to summarize this section. The Well-Architected Framework provides best practices and design guidance, and its lenses extend guidance to focus on specific domains. You can use the Data Analytics lens to guide your design of data pipelines to suit the characteristics of the data that you need to process.